Hello and welcome to EP2P04 topic number 10, beam resonance. This is a really advanced thing to be able to tackle in second year, but thanks to the tools that we've developed, we can actually give it a shot. All right, so what are we looking for? We're going to be combining this stuff that we dealt with for resonance at the start of the course with mass spring systems and all the beam stuff that we've been doing to understand beam resonance. The main goal this time is going to be just to determine the mode shapes and the frequencies for small amplitudes of these beams and do this both analytically and in FlexPDE for all kinds of crazy boundary conditions that we can come up with for this thing. If we have those frequencies and mode shapes, then we're going to know how the beams will respond, and that will tell us how they're going to behave in a variety of different physical situations. This is pretty cool. For a mass on a spring, it really just has a resonant frequency, and the mode shape, the shape that it deforms into, is just up and down. It's like a one-dimensional object, right? But now we're going to find that by having a continuum object like a beam, you'll have an infinite number of frequencies. You're guaranteed to have an infinite number of resonant frequencies, and you have an infinite number of mode shapes, although the lowest frequencies turn out to be the most important because it takes so much energy to have any appreciable amplitude of oscillation in the higher frequency modes. So let's get cracking. Consider again a differentially long, a dx long little segment of a beam that has the shear force and bending moment applied to it like this. So we've got a shear force and bending moment on the left at position x, and then at position x plus dx applied on the right in opposite directions. These are applied by the pieces of the beam to the left and right of this little segment, respectively. In topic 8, we worked out that the angle that this makes with the horizontal is related to the slope of the vertical displacement, the transverse displacement. And for small displacements, this direction is always just in y if we're extended in x here. The internal bending moment is related to the curvature that we get. Again, the curvature being the curvature in the y direction now. And this is related through the flexural rigidity from our bending Hooke's law. The moment that is applied at any point internally is EI flexural rigidity times the curvature, where curvature is the second derivative of the displacement, and that the internal shear force is the derivative of the bending moment along the length, making it the third derivative of the displacement multiplied by flexural rigidity. If you don't have a distributed load, then the net force on this segment is V up minus V at x plus dx, so V at x minus V at x plus dx, which is negative del V by del x times dx by a linearization as usual. And taking the derivative of V then, we end up with negative EI times the fourth derivative of displacement with respect to x times dx. Previously, we had, in addition to this, a distributed load acting on this thing in the downward direction. And when we brought that over to the other side, we got the beam equation. So we said the beam equation came from saying this total net force is equal to 0 if it's in static equilibrium. So we can equate this to the distributed load and use it to solve for the displacement. Now, suppose there isn't a distributed load. It would be pretty boring. It would just say that V is equal to 0 if we're using statics and saying the net force is equal to 0. But what if the beam is accelerating, and instead of saying that the net force is 0, we say that it's the little bit of mass of this segment times its acceleration? For this little bit of a segment, the bit of mass is the mass per unit length mu times dx, the length, the little differential length that it has. So if we substitute that in, a little bit of force is mass per unit length times dx, then what do we get here? We get the let's go and work in a different spot. We've got the little bit of force is equal to this, and we know that the little bit of force is equal to this thing that we worked out from the change in the shear force. So then, we can substitute in the little bit of mass as mu dx, and then the dx cancels, and we've got this. This thing is the dynamic beam equation. You heard me accidentally say dynamic beam equation a few times when we were dealing with the beam equation. So this is a partial differential equation, not just an ordinary differential equation like the regular beam equation, but this one expresses the idea that the displacement could be a function of not just position along the beam, but of time as well. The solutions to this are the harmonically oscillating bending modes of the beam, each oscillating at a corresponding resonant frequency. We'll look at solutions to this to see what those are and where they come from. Like with bending before, we're going to say that the vertical displacement doesn't depend on where on the cross-section we are, and we're ignoring the horizontal displacement there, so we don't care about the twisting of this thing. We're going to say most of the energy is just in the moving up and down of this thing, at least for small displacements. You could have a look at a little bit of torque on this from the moments and work out that it isn't that much to worry about. So we've got a difference in moments on this, which from a linearization is del m by del x dx, and then the shear force at one side and the shear force at the other side. This is finding the torque about the center. So we have a dx over 2 for each of those in calculating the torque. Then we have a linearization on this shear force leading to a del v by del x dx term that sticks around. The dx over 2 from each of these goes in the same direction with this regular shear force. So we end up with a v dx, but because v is del m by del x, this cancels with that. So you have that the net torque on this thing is only del v by del x times dx squared, and dx squared is very small, so the net torque ends up being not much of a factor compared to what's going on with the vertical displacement. Now this differential equation is fourth order in position and second order in time. The position stuff gives us means we're going to need boundary conditions like we had before to solve it, and these work exactly the same as they did in the beam equation, where you have a fixed support, and that tells you that the displacement and the first derivative are both equal to 0. The v at x equals 0 and the del v by del x at x equals 0 are 0, whereas a free end with no moment and no shear force would tell you that the second and third partial derivatives of this with respect to x are 0. But now, because of the time dependence, we also, in general, to solve it, would need two initial conditions. What v at all locations in time 0 is, and what the rate of change of v in time, the vertical displacement, is at time 0 as well. Before we look at how to solve this thing in general, let's just explore a solution to this. So if you have a cantilever, which is a beam that is fixed at one end, remember, and otherwise free, the differential equation that you'll be solving for the dynamic beam equation is something like this. So here are the boundary conditions you'd have for a cantilever. At 0, you have no displacement. At position 0, you have no displacement at all time. The wall position can't move no matter what time it is. Right. The slope at 0 is also 0 for a fixed support. It's not a pin that can rotate, it's just fixed to 0. What about the far end? At L, because it's a free end, we have no moment applied there, so that leads to the second partial with respect to x, which we'll show with these two x subscripts here, is equal to 0. And there's no shear force applied there either, so that means the third partial with respect to x at that end of v is equal to 0. Yes. So that's the set of boundary conditions, but we also would have initial conditions. Let's just keep those general. We'll say initially it's been given some deformation, f at x. This is at all x and time 0. And its velocity, the velocity at which it's crossing the axis at time 0, let's say, is equal to 0. So this is, well, I mean, it's not crossing the axis if it's not at the axis, but the velocity that it has at time 0 is 0. So this would be what the set of boundary and initial conditions would be if it is released from rest. So released, meaning not given an initial velocity or pushed or something, but it's just released from some deformed position at time 0, and we expect the beam to kind of oscillate back and forth in time forever unless there's damping in it, but in reality there is damping. We didn't put in that damping, but there would be some internal damping force that means the beam wouldn't oscillate forever. So this differential equation, by the way, is a linear partial differential equation because we don't have any v squareds or cos or sines of v or anything like that. So if you have one solution for v that makes the right-hand side equal the left-hand side, and you have another one, and you add them together, then they're still going to be solutions. So this has the solution in general, which is a linear combination of all of the resonant modes, Vn at xt, given a subscript n there. Some linear combination of them, meaning we're just going to take all of them, multiply each one by its own constant, and then add them all up. And that is a linear combination. So any solution to the cantilever position versus time can be expressed as a linear combination of its infinite resonant modes in time, each oscillating harmonically according to some cosine at a specific frequency that depends on which mode we're talking about. So we've got some cosine with some phase shift depending on how it was excited. And this is all going to be given one constant that depends on the initial conditions. So what do the mode shapes look like? This is the mode when you take the mode shape and you oscillate it harmonically by multiplying it by a cos function. This thing by itself, the thing that only depends on x, is the mode shape. For a cantilever, it turns out that the mode shape looks like this. So what do we have here? We've got some constant that looks complicated, don't worry about it. And we've got a cosh and a cos and a sine and a sinh. All right, so a sum of trig functions and hyperbolic functions is going to give you this set of mode shapes. What are the betas in here? The betas are the roots of this equation. Cosh of beta L times cos of beta L plus 1 is 0. And the frequency is related to this beta. If you know what beta is, and you know what the beam's flexural rigidity and mass per unit length is, then you can figure out the frequency. Now let's compare this to what we had for a mass on a spring. The frequency that we had went like a root k over m. And for this beam, the spring constant is kind of like the flexural rigidity, right? This is a bending phenomenon. So this is the resistance to bending. This is like the stiffness, the spring constant. And the mass would be the mass per unit length that we're talking about here. So this is a lot like your root k over m that we had for just a mass on a spring. I just made some touch-ups to this figure. Previously, it was going into the wall at what looked like an angle. So you can show you what that looked like. This one, it was not quite correct and could be misleading. It should have zero slope at the wall. So I've gone and replaced it with this one, which now has zero slope on the wall. So this makes, you can sort of see it keeps adding extra nodes. We've got no node except for at the wall. And then we've got one node here with a bump and then an extreme. And then we've got a solution with two nodes, one node there, and there it makes it to the end. This is a bit of a sketch up, and we'll look at the real solutions later, but this gives you the idea. The extra cantilever modes end up having displacements that kind of cross back and forth, and because they don't go all in one direction like the fundamental mode, this one ends up having a lot more displacement from equilibrium for a given amount of elastic energy required, so is much more dominant in terms of the overall response that you witness. So let's explore this. Let's find out what the fundamental resonant frequency is of the that is the resonant frequency of the fundamental mode of the cantilever in terms of E, I, L, and mu. Well, we know that the resonant modes of the cantilever are going to be oscillating according to this shape, where the beta n are the roots of this equation. Beta n is the nth root of this equation. So let's plot this versus L. What we can do, not versus L really, let's plot it versus beta L. So we know that we're looking for the beta L that are the roots of this. So let's plot beta L. Oh, let's put in the function. So we'll say generating function is equal to cosh of beta L times cos of beta L plus 1. And what we want to know is where is this equal to 0? So let's plot the generating function from beta L is equal to 0 to, I don't know, 5. Let's see. Okay, so this is showing us what the values are of this function. And we want to know what the roots are of it. So we want to know where it's equal to 0. It looks like we've got a solution between 1 and 2. So let's get that. We'll say beta L1 is equal to fsolve, generating function from beta L equals 1 to 2. And sure enough, it's 1.875 is the solution for this beta L. That's what we need for the first root of this function. Now, when we have that, we are going to have V1, which is what we get when we substitute beta L1 into this equation. So that would be cosh of, okay, so hold on. If this is beta L, what's beta? Well, beta 1 would be beta L1 divided by L, whatever L is. And so then V1 would be equal to cosh of beta 1 times x minus cos of beta 1 times x. You know what? Let's just say that, let's put in the general one first. Let's say that V is equal to cos of beta x. Let's put this in without beta subbed in for beta n, and then we'll substitute it in so that we can quickly get a few different solutions and compare them. So we'll just type out this equation, leaving everything in terms of beta and x, plus this thing here, cos of beta times L, plus cosh of beta times L, all over the same thing but sine and sinh. And then we're going to multiply that by sine of beta times x minus sinh of beta times x. All right, so here is our function. The L is known. That would be kind of a constant for any given cantilever. This is like the length of the cantilever. And we've got our beta in terms of L. And we could say now V1 is equal to subs beta is equal to beta 1 into V. Let's have a look at that function. So it's dependent on the x over L, and it's got this 1.875 thing that we substituted in. We could evaluate this as a floating point number. And that is just going to clean up the coefficient of the sine and sinh terms by combining these things together. So this is all known at this point, and we could get that. So depending on what L is, we're going to have this thing that scales along the length of the cantilever. So regardless of what L actually is, let's say L is equal to 2.3. If we were to plot V1 from x is 0 to, whoops, logged out there. All right, we've hacked back in. So we're going to plot V1 from x is 0 to L and have a look at this. So here is the deformation of the first mode of the cantilever. What about the second mode? To find that, we would get the second root of this equation. So this is this generating function. It has another root you can see between 4 and 5. Beta L2 is equal to fsolve the generating function. Beta L equals 4 to 5. And then we could, again, with this thing, get the beta that we're looking for and substitute that in. Let's just suppress that, and we'll say V2 is subs beta is equal to beta L2 over L into V. And now we're in a position to plot V2. Let's have a look at that one. Aha, another resonant mode of the cantilever. Doesn't matter whether it was positive or negative, kind of goes up and then down. This is the real shape of it, not this kind of like artist's rendition. The artist is me, so it's not nearly as good as the real shape here. Can you find the third mode? Is there a third one? How would we do this? We'd carry this function out further. Maybe instead of plotting to 5, let's plot it to, I don't know, 9. It's getting a little bit tough to see there, but past 5, there's another route around 8. One thing you can do is instead of plotting the generating function itself, you can plot the generating function divided by beta L, and this will make a different version of it that has the same roots. Did we plot that differently? Let's go divided by beta L squared, maybe? Oh, that's odd. Oh, because that goes to 0 at the start. Maybe we won't start it at 0. We'll start it at 1 now. Okay, cool. We've got this root at 2 and a root around a little bit before 5, and it looks like a root a little bit before 8. So we can find beta 3. Beta L3 is the same thing, but we're going to go on a higher range. So we're going to look in this function, cosh of something times cos of something plus 1 equals 0. There's another root of this when the something is between 7 and 8. We can find out exactly what that is, and it's 7.85. If we take that thing we found and we substitute it in, after dividing by L, that'll give us the beta 3. And then we can find a third mode. And we can plot this as well. Aha. So again, it has no slope at the end, quickly curves up, and then moves up like this. So this is the third mode shape. You could continue like this and find any mode shape you like. Let's find just one more. This is kind of fun. Hope you're enjoying this. So, because it is definitely fun. I'm certainly enjoying it. So we're going to go between 10 and 12 here and plot one more function. Find one more root for this. Beta L4, solve the generating function on 10 to 12, and then substitute in the 4, beta L4. Yeah, once you get the hang of it, it is pretty quick. There's not a huge amount of things we need to change to get another root of this. And there we go. So this is the fourth mode of this thing. That's kind of fun. So this is a bit of a sidetrack, but especially, I think it was pretty fun anyway. This is asking us to find really the fundamental mode frequency so far, and we didn't actually do that. The mode frequency is beta squared times root EI over mu. So if we wanted to know the fundamental frequency, we would just take this beta L1, divide by L, and then say omega 1 is equal to beta 1 squared times square root of EI over mu. And we get that it is this thing, 3.516 root EI over mu over L squared. So the frequency of the beam will decrease with length squared. It will depend on flexural rigidity divided by mass per unit length. We can get a little bit more specific about that if we assume it's got a rectangular cross section. Let's say that EI is equal to E times H cubed times B over 12, and mu, the mass per unit length, is going to be rho, the density times B times H. Then what is this going to turn into? Should the width matter for the frequency? No, just the thickness should matter. So the width is going to hopefully cancel from this mass per unit length and the flexural rigidity. And let's see what we get. Oh, we have to ask it for omega 1 again. Let's check that out. Omega 1, and we get this. So here's our omega 1. We have it scaling overall like the thickness. So the thicker the beam, the higher frequency it's going to have as its fundamental mode. The stiffer and denser the beam are going to lead to higher and lower frequencies by the square root of the stiffness and density respectively. And the length, again, is going to have a huge effect on the resonant frequency. So if you make it 10 times as long, it's going to have 1/100th of the resonant frequency. That means that if a 1 meter beam resonates at 1 hertz, like 1 cycle per second, then a 10 centimeter beam that has the same cross section, everything else is the same, is not going to have a 1 hertz frequency, but is going to have a 100 hertz natural frequency. So it's going to go up by a factor of 100 if you make the length a factor of 10 shorter. The next example was to find out the mode shape, and we did that. We took this function and we took the beta that we got and substituted it in order to plot that, and found a shape kind of like this. Next up, we can say, suppose we have a specific set of dimensions, 1.5 meters long, 20 centimeters wide, 10 centimeters thick, and it's made of steel with these parameters and this density. Okay, so it's not steel. Steel would be about 4 times as dense as this, but otherwise it's like steel. Then figure out the fundamental resonant frequency. Okay, well, all we have to do now is take this formula that we figured out and put in what the parameters are. So we'll imagine that L is equal to 1.5. H is equal to, which way is it oscillating? So let's imagine that Z is the thickness direction and Y is the width. Why would we say that? Because the thinner we choose for H, the lower the frequency. Let's see. Remember that the frequency was proportional to H. So the lowest frequency, the fundamental frequency, is going to be the one where it's oscillating in the Z direction because it's thinnest in that direction. E is 210, E9, nu is 0.305, rho is 2000, and that should be all we needed to do to now have an actual number for the resonant frequency. So 462, this is omega, so it's not in hertz. This is in cycles per second. 462, hertz is cycles per second. This is rads per second. 462 radians per second. What if we want to convert it to hertz? We say, I don't care for rads. What are these? Give me the hertz, man. So then what you'll say is F1 is equal to omega 1 divided by 2 times pi. And there we go, 73.6 hertz. So 74 cycles per second corresponds to this 462 radians per second. Picture this. You get a 1.5 meter long beam that has the stiffness of steel but is lighter and has a width of 10 centimeters. And you hit this thing and it's going to make a sound like 74 hertz. Here's a site that you can use to hear what 74 hertz sounds like. This is not necessarily what the beam would sound like in its entirety, because at least at first you're going to hear the higher frequency responses too. So when you, if you hit it in the right direction to excite this thing, then you'll hear that 74 hertz. What if we had it oriented the other way? Now this is going to respond with 147 hertz. So the fundamental frequency is the lowest frequency that the beam is going to be able to respond to. And for an arbitrary setup of the beam, if you don't know which way is the thickness direction, the fundamental frequency will correspond to the minimum thickness, because that's what's going to give you the lowest frequency. Well, that's all well and good for the solution of the cantilever, when we just say that this is the solution where beta is the nth root of this thing and the frequency goes like that. But where does this come from? And how do we solve the beam equation for something that's got different boundary conditions? What if it's not a cantilever? Then how do we deal with it? Well, that's what we're going to do next. We're going to work out the general solution to the dynamic beam equation. Here's how we're going to do this. This uses material from the end of Math 2Z when you do partial differential equation solving. First, you assume a separable solution, one that's just a product of a function only of x and a function only of time, only of position and only of time. There's no reason that this should necessarily be the solution, but because it's a differential equation, we can start this way, find a solution, and then if we can find an infinite number of solutions like that, we can just form the general solution by adding them all together and get all kinds of flexibility that way anyway. So let's just assume that we can find solutions like this. This was the form that the Cantilever solutions happen to be in, right? We said that the general solution was a linear combination of all of these things where each one is this function of just position and a function of just time, this harmonic term. So that's what we're going to do in general. Then we're going to substitute this thing into the partial differential equation, and then we're going to separate it into ordinary differential equations in position and time. This will work as long as we have the right kind of partial differential equation, and there's some work that you do in math to see when that works and when it doesn't, and then use the boundary conditions, initial conditions, and linearity to solve the ODEs that we're left with and find a solution to the original partial differential equation. Well, that's at least how we would do it in Math 2Z. In this course, we're going to skip a lot of this and just assume a harmonic solution right at the start. So we're looking specifically for solutions to this beam problem where we don't just have a general function of x and a general function of time, but specifically the function of time is cos omega t plus phi, some arbitrary frequency sinusoid. When you substitute that in to the differential equation, let's do this manually actually. We've got this differential equation, and we're going to substitute in this function. So what do we have? We've got no derivatives with respect to position on the left, and no derivatives with respect to time on the right. So if you take this thing and you put it in there, you'll be able to take some functions out. So this thing here doesn't depend on time. This is just our function of position, so we can take that out of the derivative. And over here, the cosine term has no position dependence in it, so we can take that out. Now on the left, we're left with a second derivative with respect to time. And if you take two derivatives of the cosine function, you get negative omega squared times that same cosine function back. On the right-hand side, we just are going to stick with our fourth partial derivative of v hat. Now, though, we can cancel the cosine, because in general, the only way to have the left-hand side equal the right-hand side for all time is if, because cos is not always going to be 0, is if the rest of this stuff is equal. So that means we've ended up with a fourth order differential equation that we need to solve just in v hat. So this says v hat at x, by the way, oh yeah, because this is only a function of x, we can write the fourth derivative as just 4 primes like that, right? So we've got v hat at x on the left times negative omega squared is equal to negative vi over mu times the fourth derivative there on the right. Okay. Or, if you like, the fourth derivative of the function times ei over mu times omega, ei over omega mu, has to be equal to v hat. So here we go. Oh wait, I dropped a squared. Omega squared. Yeah. So this is it. This is the thing that we can next solve. This is an ordinary differential equation for v hat. How do we solve this ordinary differential equation? Well, the way you can solve this in Math 2Z03 is by assuming, because it is a linear homogeneous fourth order ordinary differential equation with constant coefficients, you can assume a solution that's just an exponential and substitute it in, and then find out that there's 4 different possibilities for what this r exponent has to be, the coefficient of x in the exponent. It will be the solutions to this equation. R to the 4 is equal to omega squared mu over ei. And there's 4 different possibilities for that. So once you form those 4 different solutions, once you take that as the r values, you can rewrite this by saying, hey, you know what? Rather than exponents, I'm going to rewrite this as a sum of the two real roots. So e to the positive real root plus e to the negative real root over 2, but that's just a cos hyperbolic. So we have that function by our e to the this plus e to the this. And if you take the difference between those, you get your sine hyperbolic. If you take the sum of the ones with the imaginary roots, you have cosine. And if you take the sum of the ones with the imaginary roots and divide by 2i instead of 2, then you get sine. So we have 4 more convenient functions than e to the just these things with some complex numbers and some real numbers by combining them and writing out cosines and sines, where again, we can make a more convenient thing. Rather than writing the 4th root of this thing, we'll just write beta as that. This tells you why omega was related to beta in the way that it was for the cantilever, right? So if beta is the 4th root of this, then that means that beta to the power of 4 is equal to omega squared mu over ei. And it tells you that omega must be equal to the square root of beta to the 4 ei over mu, or beta squared root ei over mu. So then what we need to do is just apply each of the boundary conditions that we have in turn to find out what these c's are. The way that this is always going to work out is we'll use the first 3 boundary conditions to find out 3 of the c's, and we'll use the 4th boundary condition to find out all the betas that will work. And by choosing this as our solution set, there's always going to be an infinite number of betas that will solve things just like there was for the cantilever. That's why, by the way, the cantilever condition to generate all of those betas ended up being this funky looking thing that involves cos hyperbolics, cosh, and cos of beta times L. Because when you substitute in your boundaries for x on this thing, after getting rid of the other coefficients, you'll end up with exactly that kind of equation to find out what all the betas is. We'll look at an example of that in just a moment. Let's summarize. To solve the dynamic beam equation, subject to some set of boundary conditions and initial conditions, what you'll do is assume a harmonic solution, then substitute it into the partial differential equation, which leads to this ordinary differential equation, and this has this general solution for this set of betas. Then you can substitute 3 of the boundary conditions into this to find out what 3 of the c's are and eliminate those, and use the 4th one to find a generating function that simplifies all the values that specifies all the values of beta that will work. Sometimes it will give you a closed form solution like sine of beta equals 0, so the betas are just n pi, but often it'll be some implicit function like cos beta equals 1, and you have to use fsolve to find out what as many of these betas as you like are. Once you have them, you can sub back into this thing after you've solved for the other c's and find out what the resonant modes are, because you're later going to be taking a linear combination of these to form your general solution to the dynamic beam equation. It doesn't really matter what the overall constant multiplying the mode shape is. We're just looking for the shape of the function, not the size of the function, right? So if you see one that is positive and one that's negative, it's telling you the same shape. We're just saying it oscillates between that thing and negative that thing. That's what's really going on when we look at these cantilever modes. So in this, where did this go? Oh, we're plotting on the wrong range, plotting up to 2 here when we put x equals 1.5. Yeah, so L was 1.5 when we generated it, and then we changed it later and changed the plotting thing. Yeah, here we go. So really what these would do is it would oscillate between going to that shape in red and going to negative that shape. Oscillate back and forth. What about the green one? It would go between that and flipped. So down and up. Yeah? And same thing with the yellow one. It'll go between that and that thing flipped. And the blue one will go between this thing and the thing flipped, oscillating back and forth between those shapes. Let's plot maybe just that. Let's say V1 and negative V1. Right? So it oscillates between these two extremes. Maybe we'll even go 0.5 times V1 and negative 0.5 times V1. oscillating between all of those things and even the origin, which would be 0 times V1. Oh, that doesn't really show up very well. But yeah, all of these different shapes is what it oscillates between. Then you could say V2 is V, or V1 is equal to V2. And now we'll be plotting V2 instead. So this is the first harmonic, which is the second resonant mode going between this shape, boom, 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 like and back and forth. And you see we've got a thing there. This is a node. That's what we're talking about when we look at these shapes, because remember, we're going to be multiplying them by cos of omega t plus some phase offset. So when you multiply that in time, this is what it does. It oscillates between some value and negative that same value in time. And the thing you're scaling it by is just the amplitude. That doesn't change the shape. Okay? So next, what about V3? Let's show what that oscillating would be. Now you see what I'm talking about with the two nodes. Anywhere the resonant mode shape is at the origin, it's still going to be at the origin when you multiply it by some constant. So that tells you it was a node in the original mode shape equation. Yeah? So once you've got those modes and the corresponding frequencies, you could form the general solution by taking the linear combination of all of them. And then once you have this, you'll be able to satisfy the initial conditions using stuff like Fourier series in Math 2 ZZ3. But we're not going to be doing that. We're just going to leave it at finding the modes and their corresponding frequencies and say, oh, that's good. That shows us stuff about what the beam is doing. We don't need to know a particular response pattern that it will have when it's given some initial excitation to still know some interesting things about the beam. By knowing what its resonant modes and corresponding frequencies are, that tells you where it's likely to respond a lot if you think back to the stuff that we learned about mass spring systems earlier. The difference is this is like knowing how the thing could respond and what the resonant frequencies are, and doing the next step is like knowing what a particular response curve looks like for a given set of excitations. So let's go and try and apply this process specifically for a cantilever and see if we can derive that the solution for the cantilever should be this set of mode shapes where beta n is the root of this generating function. Okay, to do this, we're going to apply this set of boundary conditions and apply it to the solution to this differential equation, which we've said was already this. So if we apply this one step at a time, we will be having a bunch of different equations. So the notes show you how to do this analytically. Let's talk through this thing with Maple, though, in the video. So we know that if we were to substitute in a harmonic solution, then we're going to be led to this ordinary differential equation, which we can try to solve. So let's try to desolve omega squared times v hat is equal to ei over mu times diff of v hat. V hat is going to be a function of x. With respect to x, 4 times. So we have 4 different constants in front of these things, but it has opted for the exponential terms. So remember the imaginary root and same thing, but without the negative, and the negative real root and the other root. So we don't want this one. Rather than doing this, we're going to just start with the v hat already put in the nice form, which is c1 times cos beta times x plus c2 times sine of beta times x plus c3 times cos beta times x plus c4 times sine hyperbolic of beta times x. So we're going to say that this is what our v hat is, which is a simplification of that more general form where beta is defined as the 4th root of this thing that depends on the parameters. Now we're set up for success, so we can apply the cantilever boundary conditions. Cantilever boundary conditions say that at x equals 0, we have 0. So let's try substituting that in. Subs x equals 0 into v hat. And then what you do is sometimes people are really confused by this process because they just look at the final code, and the final code is not going to make a lot of sense. You've got to do this process looking at the output all along the way. So we're going to sub x equals 0 into this thing and just have a look at it. Okay, when x is equal to 0, we get that. Let's in fact simplify it. Simplify, substitute x equals 0 in. Aha. Now we need this to be 0 by that first boundary condition. So let's say that we're going to solve this thing equals 0 for C1. Why not? And we'll say C1 is equal to what we get when we do that. All right, now let's recap. What's v hat now? C1 is known. See that? It's substituted in. Next up, we can go and apply the next boundary condition. So let's say simplify subs x equals 0 into, actually, you know what? Let's find out what the derivatives of this. So we'll say v hat prime is equal to diff of v hat with respect to x. V hat double prime is a second derivative, and v hat triple prime is equal to the third derivative. Okay, now we'll say that hold on, let's not jump the gun there. Let's simplify, substituting x equals 0 into v hat prime. And what do we get there? When we substitute that in, we're going to have beta times C2 plus C4. And we need this to be 0 as well. Well, we don't want to make beta equal to 0. So let's substitute this into that divided by beta. And we'll say that this thing has to be 0. What are we going to solve that for? Let's say that C2 is equal to solve this thing for C2. Now we've got C2 has to be -4. All right. And now we can recap v hat again. Now we've solved two of the parameters. C2 is not -4, -C4. Okay, we got -C3 for C1 and -C4 for C2. All right. What next? Well, the next boundary condition is that v double prime at L subs x equals L into v double prime. And let's have a look at that. Whoops, v hat double prime. Okay, this thing has every term scaling like beta squared. So let's say that this over beta squared has to equal 0. How will we do that? First, let's simplify and let the beta squareds cancel. And we can solve for any one of these coefficients that we like for C3 or C4. Sometimes it can go wrong. Let's just guess. We'll say C3 is equal to solve this thing for C3 and see what we get. So that's going to say what C3 is. In terms of C4, we're going to be dividing by cos plus cosh. And now we've got that v hat is equal to this thing. Let's try to simplify on v hat. Oh, that didn't look very good. Okay, never mind. Just regular v hat. And what do we got? We got some crazy thing with C4 in every single term. So now there's only one more parameter left. And now we are ready to get our generating function. So the last condition is that v hat triple prime, when x is equal to L, is supposed to be equal to 0. So this thing has to be equal to 0. Let's simplify it and see what it looks like. Okay, so we need this to be 0, but we don't want to make v hat always equal to 0. So we're not going to take C4 equal to 0 because that's all we had left, right? V hat at this point looks like this. So C4 is in every single term. If we take C4 is equal to 0, then we don't have any mode shapes. We've just got the trivial solution. So forget that. And similarly, we don't want to just put beta equals 0 because that's also the trivial solution too, if it's a solution at all. So rather than just doing that, let's find out how else we can make this equal to 0. We could make it equal to 0 if this thing is 0, right? Does that look familiar? So therefore, all we need is that this thing is equal to 0. And that's where the generating function comes from. So then, the solutions are going to be v hat, which are these things, where beta is chosen so that 1 plus cos of beta L, cosh beta L, is always going to be equal to 0. So we can take v hat and divide out the C4 because we're just going to be scaling the solution by that, so that thing doesn't matter. Another thing you can do at this point, rather than just dividing out the C4, you can say, let's just scale it to C4 is equal to 1, and look at v hat. And now that C4 thing is gone, and you see this is kind of similar to the cantilever solution, except now we've got the sine and the sinh outside of this term that involved the coefficient, and it's the cos and the cosh that are inside of that. And that has to do with which parameters we solved along the way, but actually it shouldn't be any different. So we can go now and find out what beta 1 is. So for instance, let's pick a value for L. So let's say L is equal to 1.73. Why not? And then we will plot the gen function from beta equals 0 to, I don't know, 7. Too much. Let's go from beta is 0 to 3 and look for the first root. It looks like it's between 1 and 1.5. So we'll say beta 1 is equal to fsolve gen function from beta equals 0 to 2. And then maybe we'll say beta 2 is equal to fsolve generating function from beta is 2 to 3. Sure, we found a couple of roots there. And what do we find? We find those things which don't look familiar, but if you were to multiply them by the L that we have, they'll be exactly the same roots that we found earlier, 1.875 and 4.694. Yeah, so if you take those and substitute them into the V that we have, we can get V1 is equal to subs beta equals beta 1 into V, and have a look at that if we like. Into V hat. That's why it's good to look at it even if you don't think it's going to be that nice of a function. And then we can plot that from x is 0 to L, along with V2, let's say. And plot V1, V2, x equals 0 to L, and just see what we're looking at here. Well, that's the same mode shapes as we had before. Looks like they're flipped. Again, doesn't matter. They're the same mode shape because what you're going to be doing with them is multiplying them by that harmonic term. So even after you multiply them by that harmonic term to get the modes, you're going to be taking a linear combination of all of that to find the actual solution. So not only does the sign of this function not matter, but the size of it doesn't matter either. It doesn't matter that we're going to a slope of like 2.5 or 3 this time, whereas the last time we did this, they were scaled to a different height. Totally doesn't matter. They are the same shape, and that's what counts for getting the actual solution. So all we need, that's why we're calling this a mode shape. We're looking for the shape of the curve, not the size or the sign of the curve. All right, let's try a different problem rather than a cantilever. In first year, you were able to find the resonant modes of a guitar string of length L, mass per unit length mu, and tension force Ft, and that those were sine functions like this. So you took guitar string modes, and maybe you did this in high school too, but you've got sine functions which are going to be the mode shapes that we're looking for, maybe scaled differently than this. This is just showing that they all kind of line up at different spots there. Now, can we end up reproducing the same thing in the dynamic beam equation. I mean, a string is not quite a beam, but what about a beam that's pin supported on each end? Will we have anything in common with what's going on with the guitar string modes? First of all, what boundary conditions does it have? Well, it's kind of like pin supported at each end, we said. And so what does that mean for the displacements that we get? That means we are going to have a fixed value of 0 on each side and no moment on each side. So that means no second derivative on each side. Next, can we substitute the boundary conditions in and find the resonant modes for a guitar string, or at least for a beam that has pin supports on each end? Let's see. Well, we'll substitute in, we'll do the same process as we just did. So let's try subs x equals 0 into v hat. Actually, this first one is going to be exactly the same. So let's use that to solve for C1. And then what we'll do is we'll substitute in subs x equals 0 into v hat double prime and have a look at that. When we simplify this, that tells you that we actually need no C3 term either. So C3 therefore has to be equal to 0. What about, so what's v hat now? Something even simpler. What's the next boundary condition? Well, we can substitute in that when x is equal to L, we have no displacement, right? So when x is equal to L into v hat, we need this to be equal to 0. So let's see if we can solve this for one of the parameters. We can solve for either C2 or C4. If you solve for C2, you're going to run into trouble. I'll show you what happens here. Let's solve this thing for C2 and say that that's equal to C2. The problem is we're dividing by this sine function, and this is going to be giving us zeros at a bunch of different spots. So now, and this will only work if it turns out that sine of beta L is non-zero. But this is 0 at a bunch of different betas, right? And in fact, now the problem is the cinch cannot be, well, you'll see what happens here. So what's the last condition? We'll say subs x equals L into v hat double prime. And now that we've done this, we need to have this thing equaling 0. But we can't. We can't have the sine hyperbolic of this thing equaling 0 unless beta equals 0, and we can't have the beta squared equals 0. So that's no good. So forget that. Where it went wrong is when we substituted, when we said this thing, let's solve it for C2, that assumes that sine beta L is equal to 0. And it turns out that actually what you need to do is solve it for C4 and then substitute x equals L into v hat double prime and apply that this condition is equal to 0. So once we've solved this thing for C4, now we've got v hat that looks like this thing, known for C4, and when we take two derivatives of this and then substitute in an L, the sine hyperbolics will cancel rather than the sines canceling, and we'll have just this condition that we can express in terms of sine of beta L. So now we have something that we can set equal to 0 to find all the betas. So the generating function is equal to sine of beta times L. And that means that all the betas are this closed form thing. All you need is that beta L is equal to n pi, which means beta is equal to, so beta n, beta is equal to n times pi divided by L. And that gives you all of the different betas that we're looking for. So now we can just say, if n is equal to 1, then we're going to have v hat, which looks like this. It's just a sine function. What about if n is equal to 2? Then we've got that different sine function with twice the frequency. We can plot a bunch of these. So let's say plot subs n is equal to, or how about this? How about we say v1 hat is equal to subs n is equal to 1 into v hat. v2 hat would be substitute n is equal to 2 into v hat. Let's see if that's working. Oh, we didn't give it a range on plot. We'll have to do that. Plot this from x0 to L, and we probably have to say what L is. Let's say 1.2 this time. Should be able to be anything and still work. Oh, that didn't work. I didn't plot because it doesn't know what C2 is. So we need to tell it what C2 is, and it doesn't matter. We can scale C2 however, so let's just say that it's equal to 1 at this point. And now we've got our two functions, and they look just like the guitar string modes. So for the pin at each end, we have the same thing going on as we did for the guitar. What about the frequency? So the frequency that we're going to have for this thing is omega is equal to, as before, beta squared times the square root of EI over mu. And we get that the frequencies go like n squared. So this time for this beam, we don't have just linearly increasing harmonics, but the beams have frequencies that increase like n squared. So taking the same thing and applying the beam equation rather than just the wave equation that we had for a guitar string has led to frequencies that scale with n squared rather than with n. A little bit of extra explanation. The wave equation is that the second derivative of v in time is equal to the wave speed squared times its second derivative in space. And this showed up as the response to the guitar string, because what's going on with the guitar string is the restoring force is from tension. Here we have a different restoring force, right? Rather than saying that the restoring force is from the tension along the length and looking at the angle that shows up in this thing, the restoring force for us with the beam was related to the dynamic beam equation stuff, was the shear force. But the shear force is 0 in the guitar string stuff because we just have a tension force. So the beam would behave a little bit differently if we take something that's like a beam and then put a whole bunch of tension in it and give that as the source of the restoring force rather than the Poisson's ratio coupled shear stuff that's responsible for the restoring force in our continuous beam. Really, it would be great if we could account for all of these forces together and figure out what the real mode is in a real situation rather than our idealized situation for the dynamic beam equation or the guitar string. So wouldn't it be great if we had some way to do this with finite element methods that were accounting for everything? Fortunately, we do. So just like when we were doing the beam equation in statics in topic 8 for bending, FlexPDE, we don't need to use a fourth order beam equation from the moment assumption, but we can use the full dynamic set of partial differential equations we had for each beam. Now you'll remember from the shear topic from week 7, we worked out what the net force was on this infinitesimal volume, and we said that the net force was equal to the slopes of the stresses times the differential volume element from the axial stresses, and similar things for the shear stresses on each face. So the total force in X, for example, is this sum of slope of sigma X in the X direction and the partial of tau YX in the Y direction and tau ZX in the Z direction. This is after we've already incorporated the symmetry. Really, it should be on the Y face. Yeah, this is right. This is on the Y face in the X direction and Z face in the X direction. But we know that they're symmetric too, so we didn't name them that way in FlexPDE, but still it's the same thing that we had in this differential equation there. So these are the equations we've been solving in Flex for the last few weeks. Well, this represents Now, where did this come from? Again, this is the force per unit volume, and it's led to this equation by saying that the net force is equal to 0. So just like at the beginning of this thing when we derived the dynamic beam equation and said, hey, you know what, rather than 0, let's set it to mass times acceleration, see what happens. Same thing here. Let's set it to mass times acceleration, but now it's not a mass per unit length because this was a representation of force per unit volume. So we're going to set it to the mass per unit volume times acceleration. So specifically, that means we're going to have to put in the density every time, even when we're not applying some kind of a weight force. And then we're going to have on the right-hand side, the density times the second derivative of position in each direction, of displacement in each direction with respect to time. Except that this is going to be too many differential equations for Flex to solve. The time derivatives end up needing 2 equations each. But we can do a trick by saying, again, let's assume a harmonic solution. And just like before, if we assume that the displacement in each direction is oscillating harmonically according to some sinusoid at an arbitrary phase, then the second derivative of this displacement in time is going to be equal to the displacement multiplied by negative omega squared. So what we need to use for the differential equations, the partial differential equations, is not just these things equal 0, but these things equal to negative rho times omega squared times the u's that we had. So we'll change this instead of 0 to negative rho omega squared times u, same thing times v, and same thing times w. We have to put in a density. So let's imagine a density of something, rho equals 1,000, and now, can we run it? Will it work? No, we don't know what omega is. So how do we do this? Well, we can just guess an omega. Omega equals 3, and see what happens. It gave us some kind of a deformation, even though 3 likely was not a resonant frequency of this thing. So Flex is going to make this work no matter what frequency we specify, but only certain frequencies correspond to a resonant mode, which are ones that will allow a really large displacement away from equilibrium. So the way that we're going to be solving for this, because of how FlexPDE solve things, we can find resonant modes by forcing the solution to be non-trivial, specifying a small but non-zero displacement or load at the boundaries, and then sweeping the frequency to determine where this leads to large responses, large deformations. At other frequencies, the finite element method will still work by finding the closest solution it can, even though there is no solution when we're not at a resonant frequency. The computer's outputs are just not valid, but they're the best that it can do. So this is only going to tell us that we're not at a resonant frequency by just not giving us nearly as much displacement as we otherwise would have had. We're scaling this, but the displacement that we have is very, very small. So like 1.7 e minus 3 compared to what we would get at resonance, which is theoretically infinite displacement. Let's use this approach and see if we can get the fundamental frequency for this cantilever we found analytically earlier, this cantilever in example 10.123, using this FlexPDE approach. What we're going to do is modify the differential equations to search for harmonic solutions like above. So we already did that thing, and then set a load in the W direction at the tip so that Flex doesn't just return the trivial solution, and try different frequencies and compare the results. So let's put in the parameters for this particular beam. We'll say that rho is 2,000, and we'll say that E is to 10 gigapascals, E is 0.305. We'll get rid of these stress distributions we were applying on the tip, and we've got this thing, that's good. We'll set it to fixed at x equals 0 instead. So rather than this boundary and this boundary, we'll put some small load W of -5 or something. Not very much in terms of a stress, but it will lead to a non-trivial solution here. So now what we'll do is at x equals 0, this last line to close, we'll say value of u equals 0, value v is 0, and value w equals 0. So this should give us a result for this, which is not very much. It's going to show us a lot. Oh, where did we fix it somewhere else? We've got a load on the top here. We've got it fixed on just the final surface. And we are asking for a deformation in response to almost no stress applied. Yeah, so we're hitting the numeric limit of this. There's just no displacement of this thing. Let's look at a report of W at the, whoops, there's supposed to be a W. W at the tip of this thing. So yeah, W is basically 0 there. Let's suppose instead we put omega around the resonant frequency. What about 462? Still nothing. The dimensions. So we've got to put Lx is 1.5, Ly is 0.2, Lz is 0.1. That's more like it. So now the W displacement that we were applying, the load in the negative y direction, is leading to this kind of a bending. What happens if we put omega is equal to just 4? Because we're auto-scaling this solution right now with our magnitude function, it's always going to look like a large amount of displacement. But if you look at the actual displacement that's happening, it's 10 to the negative 7. What about at 462? Well, now it's 1.5 e minus 5. We can make a plot of displacement versus position at different frequencies by first putting in a number of different stages to run the problem at. So under the select thing, we'll say stages equals, let's say 10. And here we'll say omega is equal to, let's imagine we don't know what it is, 100 times stage. So this is going to make it sweep from across different numbers. It's going to go 100, 200, 300, 400, across all the different stage numbers up to stage 10. And then in the plots, we can also make a history plot of W at Lx, Ly by 2, Lz by 2, like the middle of the end here, and have it also report what the frequency is on that if we like. So here's our plot. So as we increase the frequency, you notice something interesting happening. Right between 400 and 500, there seems to be some kind of a big spike, and the thing changes its direction. Do you remember from the resonance stuff earlier on, when you excite a system at lower than its resonant frequency, it responds in phase. We were pushing down on this. But when you excite it above the resonant frequency, it responds out of phase, right? Now, the damping here is 0, so the response is kind of magnified, and we see this at a much higher level, and that's why it kind of goes directly from in phase to directly out of phase. The resonant frequency must be somewhere between 400, because we had the frequency as omega times the stage number, and we took the stage from stages from 1 to 10 and saw somewhere between stage 4 and 5 corresponding to omega's 400 to 500, we had this resonance there. So what else can we do? We can go, we know that it's above 400, so let's say 400 plus 10 times stage and see what it looks like. Okay, sweeping down, jump up and over. We've got another displacement between 6 and 7. Now 6 and 7 now means between 60 and 70. Okay, this is looking pretty good. Now we'll add 1 times stage. We're getting a different frequency than we found in FlexPDE. It's now between stage 4 and 5 again. So we can go 464 plus 0.1 times stage. Okay, between 7 and 8 looks right. So 464.7, and now we'll change this to 0.01. And you can keep going as long as you like and get as many decimal points as you care to get. Eventually it might get kind of tricky because we have a limited amount of precision, But now you see the displacements we're getting are a lot larger. Even though we're only putting 5 pascals of force on this thing, it's responding with almost 1 millimeter of displacement because we're pushing with that force at exactly the right frequency, or at least close enough to exactly the right frequency. If you take this further, then you should get higher and higher amplitudes until you run into numeric precision. So between 3 and 4, and now it's on the order of 10 to the minus 3. Between 8 and 9 looks like the most now. Hit insert. There we go. Okay, now we have around resonance 1.6 meters of displacement. It's still scaling this automatically for us, but if we now got rid of our automatic scaling, you can see as we cross resonance, there's quite a lot of displacement there when we're exciting it at exactly the right frequency. So when you get close to the resonance, it's sometimes fun to kind of turn off the automatic scaling, and then see what kind of displacements you can get. So between 7 and 8 maybe. So let's go 7, and then add in another decimal there. These are all going to be quite large. Very magnified displacements there, and that's kind of fun. Okay, so using a few different iterations, you can zoom in as much as you like on what the resonant frequency is by looking at where it crosses the axis and modifying the frequency that you're applying to be around that point. So it's possible to find other resonant modes by having a look at what's going on in the other directions. So rather than just plotting W, let's also plot what's going on in Y, right? So in the Y direction, we can see what's happening by taking like a big sweep. Let's imagine we're going to look for resonant modes in Y, 100 times stage. It looks like there's a resonance happening in Y around that point, but this is actually just where the resonance in Z is taking place. So we might be seeing some Poisson's ratio coupling there. The difficulty is we're not actually giving it an excitation in Y except through the Poisson's ratio. So we'd have a better amount of success if we just put some small stress on it. Load V is equal to -5 as well, say. Now we can get, wow, that ran very fast. I don't know why that ran so fast. So this is showing us a much larger amount of displacement happening in Y around somewhere between 9 and 10. Let's have a zero in on that point. Right, there isn't something going on in W around that point. So let's see if we found a resonant mode that's in and out of the page there. Okay, so we're going to go 900 plus 10 times stage. Yes, look at that. We've got a mode in the Y direction. It looks like it's between 2 and 3. So that's between 20 and 30. Yeah, so there we go. We're zeroing in on this kind of a mode. We can even try to find longitudinal modes. So let's change this to omega is 100 times stage again. Maybe we won't find any, but let's have a plot at the value of, or not the value, the history of U at the end, at the center of the end, and see if we can find something where it's oscillating kind of along the length. Again, a bunch of nonsense happening here at just E-12, but if we apply a stress in the X direction, load U equals -5, doesn't have to be much, you could apply it anywhere, just on the top surface, then it becomes more possible that we could possibly find a resonant mode here. Now there aren't any in this frequency range. These are likely going to be higher frequency things. So let's change stage to the frequency range to 1,000 times stage and see what happens. Oh, we've got something. We hit something really weird. Look at this. There's a torsional mode happening. Wow. Lots of funky stuff happening there. this looks like we might be zeroing in on some kind of a longitudinal thing, but it might be the complementary longitudinal stuff that's happening from the twisting there that's going on. So maybe above 10,000, let's say 10E3 plus this. Oh. It looks like we just missed one maybe. But that might have just been that torsional mode there. So to stop a lot of these complementary modes from messing with the solution, if you'd like to specifically look for something in X, you can set up the loading so that you're going to be finding only that as your excitation. And a trick here is we'll go on the far X surface, which is this one, before we go from, wait a minute, it is this one here. When we're already at LX0 and then we're going to change Y to LY, this would be the far surface where we're equal to LX at the start, equal to LX at the end. So this is the LX surface. So we can say load U is equal to 5 and then put it back after that. And now we're going to be finding specifically longitudinal things. There's some kind of complementary flexing and stuff that happens. Did we miss one? Maybe. We're responding out of phase already. So maybe we are already above the resonance. All right, let's lower the frequency here. Let's go just 1,000 times stage and see what happens. Going up, up, up. It looks like maybe there really was one between 10,000 and just above 10,000. So this can happen sometimes. Sometimes you can just miss it by going 10,000 plus 1,000 times stage. And now you see we're just past it. So we've already jumped over it. That means it was between 10,000 and 11,000. So what do? You just lower this by a decimal and jump to the next simulation. Okay, we're rising up again, jumping around. So there we go. It's between 10,700 and 10,800. So 10,700, and we're going to add 10. In steps of 10, see what's happening. Yeah, see this oscillating between the stretching and going to this sort of shorter, fatter one there? Yeah, that is the longitudinal mode we're looking for. Let's look at that again. Stretching, and then there. Maybe we can make this a bit bigger. There we go. So you could zero in on that and find the longitudinal resonant mode. Now there's nothing special about this cantilever mode either as far as FlexPDE is concerned. We could have set up things differently and found bridge resonant modes. So we could go with something like at the other X surface here. Where is that? We could take, there we go. We'll go on this far X surface and we'll say that the values are all equal to 0. And then we'll go on the side and put the load of U equal to 0. Load V is 0 and load W is equal to 0. And now we should be able to find bridge resonant modes. So let's put in some load W is equal to 5. And we'll scale this around. Yeah, there we go. Bridge resonant modes. We started at the third mode because we left the frequency kind of high. But if we were to pick the right range of frequencies, we could zero in on these too. This is bridge supported at each of the ends. Right, so nothing special about the cantilever modes. Using this approach, you can find all kinds of things in FlexPDE as long as you're still staying linear and Hooke's law holds. We'll explore some of this stuff in the practice problems. Thanks for watching. I'll see you next time.